It's an honor to be here. One of the joys of my scientific life has been able to read and at least partially understand Roy's papers and try to apply them to my life in the lab. But even better is been able to interact with him over since 1977 we first met. So lots and lots of years. So what I want to tell you about today, maybe some of you recognize where the title came from, but some advice.
Mr. McGuire. Ben. Mr. McGuire.
Come with me for a minute. I want to talk to you. Excuse us, Joanne. Thanks.
Dustin Hoffman's me and Mr. McGuire is Roy.
I just want to say one word to you. Just one word.
Yes, sir.
Are you listening?
Yes, I am.
Plastics.
Exactly how do you mean?
There's a great future in plastics. Think about it. What do you think about it?
Yes, I will.
Upset. That's a deal.
So there's some people, when they tell you something, you need to think seriously. And Roy's papers have always been something that, even if I don't understand them completely, I need to read them because I'm going to miss the future. So plastics. What does that have to do with anything? I remind you that plastics are a subset of all dielectrics. and viewed more liberally, that's what we should be thinking about. And that first occurred to me reading this paper. So this is in not one of the papers any other speakers talked about. It's widely cited, becomes even more important in modern optical physics, quantum optics. So I want to tell you a little bit about that. This is a paper where in vacuum everybody knows how to quantize the electromagnetic field. So we need to think about a little bit what we're going to do in a dielectric. Whenever I read a paper, first thing I do is look at the title, I look at the abstract, and I say, well, this is what that paper is going to be about. So kind of what should I expect from it? And what I expect from this paper is, well, we're going to quantize a field in the dielectrics. You put an epsilon there, you get a few square roots somewhere along the way, and you're through. But that's not what this paper did. It's quantum dielectrics. 25 pages later, what could they possibly say other than put an epsilon in the right place and a square root here and there? So what they said, I won't do the whole paper, is really surprising and for reasons as we go through more and more relevant to modern research. If you, one of the examples was just have an empty cavity and then put a dielectric in it and ask what happens to something as simple as a vacuum field. Vacuum is symmetric distribution of the canonical variables, their dispersions. And what happens when we put it do the same story in a dielectric? The operators that create and annihilate and create photons in the dielectric are different than the ones in free space. Well, put a square root of epsilon here and there. No, this guy doesn't get a square root. That guy, the operators of the regular vacuum become superpositions of this in what's called a Bloch-Leibov transformation. You make photons in the vacuum in a dielectric. So how am I supposed to understand that? That's a little bit strange. So this is a paper about how do we really do the quantization correctly? How do we interpret it? If there are extra photons in there, do we detect them? Or are they more formal? Or what the heck's going on? And so we're going to talk about that for a while. The transformation of simply light going into a dielectric and coming back out in terms of our familiar B's and B daggers, A's and A daggers, is much more complicated than you might have at first thought imagined. So let's talk about that paper in the context of kind of quantum optics since the beginning, of how if we have a box and it makes light, we would describe that light we've heard about from Roy's paper in terms of his P function. And we would like to know this particular state of the electromagnetic field. Is it interesting? And interesting is it something we couldn't make by a classical current source? Is it somehow more quantum, less quantum? What does quantum mean? So we can make a single beam of light. We can make dual beams of light. In the first case, there's this over essentially one amplitude and now two amplitudes for each of the beams. So we want to talk about that. and how non-classical light came about, and what's the relevance of this paper by Lundstein and Glauber to the quantum optics of dielectrics. So a long time ago, far away in Rochester, people were doing theory that I learned from Joe Eberly and his group about how atoms get excited and the problem of resonance fluorescence. And an excited atom can radiate, and one can do Henry-Brown twists, and thanks to Roy, we know what kind of things we want to look for from the two detectors. And so Leonard Mandel and I, and independently Howard Carmichael and a former student, Dan Walls of Roy's, calculate photon statistics for the light from a single atom. And what you find is that first you have to build an experiment, and then you find, you just look at coincidences, click on photomultiplier tips. There's no working of the data. And what you find very unequivocally, just from the data, you look at this rise, that's illegal. You can't do that from any state that's made from any stochastic superposition of classical radiating currents. And that's, for a single beam, the first time one ever observed manifestly non-classical light. Okay, what does that have to do with quantum optics of dielectrics? Probably not much. This was a very dilute atomic beam that we used. So maybe we can kind of ignore that paper and go on about our business. Here's an experiment pioneered by Herbert Walter, and not in an atomic beam. Let's really get one atom, trapped ion, and look at these non-classical effects when we really know we have 1, 2, 3. So 1, you get a big effect. This little dip's what we're looking at. 2, 3, it goes up. But here's 3 ions. Surely we can't call that a dielectric. Every atom is technically a little dielectric, but we're not going to have to worry about the kind of issues in Glauber and Lundstein in this world. So likewise, for 2 beams, you can have a cascade like for Bell inequality measurements, but now we're looking at the complex amplitudes of the fields. That's the story of Glauber's pioneering work. And we're going to get 2 fields out. We're going to put each one of them on a photodetector and look at clicks over here, clicks over there. And Professor Glauber already had told us how to do that in his early papers. And this person, John Clauser, who's an absolute amazing scientist, known mostly for his pioneering work with Bell inequalities, did this experiment as part of the Bell inequalities that relates directly to non-classical field amplitudes. So what he measured was, you get a click here and a click there and a click here and a click there, and you measure cross-correlation functions. And it's required for Glauber's function is positive, that there should be some relationship between coincidences between this guy and this guy, that guy and that guy. And it's an inequality like that. I won't go through the details. But the excess here is simply a statement that for classical stochastic processes, the cross correlations have to be smaller than the autocorrelations. And so all these dots should be below there, and they're not. So wow, isn't that neat? But again, it's a very dilute atomic ensemble where only one atom at a time is emitting. And phase shifts of propagating through a dielectric are completely irrelevant. So quantum optics and dielectrics, well, maybe I should read that when I get some time. But it doesn't seem to apply to these early experiments. Oh, but wait a minute. Here's an experiment where colleagues and I generated squeeze light. And you already saw this picture in Pierre's talk about this uncertainty that comes from Malo and Glauber's early work on parametric amplifiers. And this is the domain of manifestly classical stuff. And minimum uncertainty states would follow this line. You can't go in here. Classical stuff's out in this domain, and this is all squeeze states, but you can't go past that line. And we were able to measure that some years ago. And now, I was pretty happy with this until I read Roy's paper. Some years later, you send roughly vacuum light into a parametric amplifier. This is Chi2 nonlinearity, and out comes squeeze light. And this paper, these results in the theory paper, and these results from a measurement are about this field. What the heck's going on inside here? So now there's just no avoiding, I got to read that paper and understand it. So I worried about that because before Roy had published that paper, he told me a little bit about it and heard about it in talks. And it's like, this is, we're not in Kansas. So what do you mean that, So what are we going to do about that? So we have to think about that. So in this paper, you send, quantum optics before this paper. You send squeeze light in, something happens in there, it comes out, and this is just this parametric interaction that we learned about. But in Roy's paper, you send vacuum in, you get vacuum out, and what's going on in there? Looks like it's a squeeze state, which is a term Roy makes clear in his paper he doesn't like. So I've tried to avoid using that term. What operators are physical in here? They're really, the canonical quantization leads to this really funny B plus B dagger stuff. But what would happen if I tried to detect this state inside here? I could detect its phase sensitivity inside the dielectric. I could detect its photon number. Well, it would really be weird if I put the vacuum in and started getting clicks of a photodetector inside here. So what's really going on? Well, it's just not square root of epsilon. It's really interesting issues. On the other hand, these kind of experiments, cavity QED, single or few atoms, ions and free, well, we could call it a dielectric. I drew it pretty big in PowerPoint, but really it's pretty small. So dielectric is kind of the wrong way to think about it. So maybe we don't have to, this kind of stuff we have to worry about it, but this kind of stuff we don't. And what I want to convince you is the modern world, increasingly, this is not so interesting, this kind of stuff. This is the stuff you want to deal with, as we heard so beautifully in Professor Serge Hiroshi's lecture. So what about this world? Maybe we just don't have to deal with that, but if you take a physical system and you want strong interactions of single photons, a really good system in either optics or the microwave is optical cavity, as we just heard about from Professor Hiroshi's lecture. So here's a little cavity. It's 10 microns long. And over time, you can ask, how many photons do we have to put inside this cavity to saturate one atom in the cavity, to evoke a nonlinear response? And over time, these are experiments from my group and my collaborators. We've done pretty well. We've pushed this number down from Fabry-Pros to over here about 9 orders of magnitude. And in terms of this Glauber and Lewinstein paper, you should view this axis as a length, as a size. To get the coupling, the electric field per photon, larger and larger and larger, we need smaller and smaller volumes. And as we go to smaller and smaller volumes in this cartoon, but that's the real cavity. The real cavity actually has dielectric interfaces for the mirrors. And when we get down to this domain, there begins to be as much energy in the dielectrics as there is in the vacuum. So we're doing one photon evolution, making single photons, making entangled states, we the community. And, well, that little piece, when the cavities are this long, that little piece is in the dielectric, it's good somebody's worrying about it. But when you make it like that, it's like, I better worry about that before I get the referee reports back. So necessarily in a little cavity like this, in a cavity like that, there's about equal energy in the coatings as in the vacuum. In a cavity like that, there's more energy. This is a little microtoroidal resonator. I show it again over here. There's a little microtoroidal resonator made just spectacular capabilities of Caravallo. This little thing has about a billion for its quality factor. Light runs around like that, and for years we worked to put atoms in the region of that. You couple into these, we try to get an atom right there. So around this ring, the fields look like that, and we put an atom there. And as the atom goes through, this is just this coupling of how strongly the electric field of one photon is. And this is the field profile for the electric field. And it's really small. So most of the photons that the atom is talking to live in the dielectric. Uh-oh. Single atom, but we got to worry about the photons in the dielectric. So there's the atom. I'd like to think it's in free space, and I don't have to worry about all this quantization, all these sums over modes in the Lewinstein-Glauber, but I guess I have to. This goes into a domain where this is the coupling along here. If you go near to the surface, the experiments we looked at are kind of in this domain, you get really strong single photon, single atom interactions. This graph is in the really spectacular work of Roche. But you also get Casimir-Polder interactions with the surface and enhanced and inhibited spontaneous radiation. So you go into a domain, this kind of stuff was talked about in Leuenstein and Glauber, about in a dielectric, how are radiative processes altered. Before that, pioneering experiments here, Serge Roche at Yale and Dan Kleppner at MIT. But all of this now comes into play when we try to do strong single photon, single atom interactions near or indeed inside dielectrics, the experiments of Michel Lueken and his colleagues at Harvard, where they actually have atom-like emitters inside. What are we supposed to say about those photons? We just have to, if you didn't like it, read that paper. So more broadly, I commend you to this review by Derek Chang, a former student of Michel Lueken and Vladan Vuletek. And it goes over, hey, we're really trying to get into a domain where one photon and whatever atomic system, material system, interact really, really strongly into this domain of strong atom-photon interactions. These are experiments I'll tell you about in a minute. This is the Michel Lueken's group at Harvard in collaboration with Vladan at MIT. This is experiments I'll tell you about. And other experiments, but graphene, all of these are material systems where the photons live in the dielectric. So we really need to understand better, and I've often reread your paper, all of these, I'll tell you about this in a moment. Roy's paper is based on modal expansions of the electromagnetic field, and you can get stuff analytic. This is for a linear dielectric. In all of these structures, there's no such expansions. They're really complicated. Everything has to be done numerically. So it's really hard to get good intuition about crazy stuff, like how does light get squeezed in shape inside a dielectric, a linear dielectric, from numerics. So it's good to have, as a foundation for this, the real answers, at least in some model system. So that gets us up to, we're going to do strong interactions with photons and atoms, and we're going to have to worry about the dielectrics. And from that, we're going to build up interesting quantum physics. And the way we're going to do that, polarium, I hope I say that right. Is that close? I'm from the same state as George Bush. Please. I often say I'm bilingual. Texan and English is my second language. So this is a really nice paper of, I didn't put it on there, 2000, but done earlier than that. And the idea, so far it's normal dielectrics, but we're going to put we're going to put quantum radiators near them or in them. And that's the first paper, where it was quantum optics of dielectrics. Now we want to make dielectrics that are inherently quantum at the single photon level. And this is what Roy and Prasad were doing. I assume Marlon was around somewhere. Here's light going in and out of gas phase atoms. And in this paper, this system, to try to get at some of the basic physics, was abstract the discrete atoms into a 1D continuum model. So it's just a 1D. You could think of this as infinite in this dimension, so there's only this propagation direction. And the atoms are not discrete. They just have a linear, it's a jello, and K times the 1D density is this thing called beta. And what's calculated in this and a subsequent paper is let's calculate the modes of that system, of this 1D continuum. And for some mode index, this is 1, 2, 3, 4, 5, 20. This beta is how dense is the sample. So this is a sample that's, one atom, if you want to say it that way, per reduced wavelength, and then more and more, higher and higher density. And what you see is this is the decay rate. If you put excitation in the system, there's a decay rate in some unit which is super radiant. So there are modes that irradiate faster than would in free space, and there are other modes that are absolutely dark. So as you come out here at 50, this thing's flat, 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 and then boom, super radiant, and then like that. Accompanying those enhanced decay rates are cooperative level shifts. So this is like, it's sometimes called the cooperative Lamb shift, so that there are frequency shifts associated with the atoms interacting in this discrete sample, but in this continuum model. And this is exactly what a large part of the world is doing right now, trying to realize your polarium. But with, we got, atoms come 1, 2, 3, so there's no continuum model. And so I want to tell you a little bit about that, folded into this story of, photons and dielectrics. So how do we build a quantum dielectric, in particular this polarium? Well, we're going to make a photonic crystal for reasons I'll now tell you. This one we've developed at CalTech. We call it an alligator photonic crystal waveguide, I hope for obvious reasons. This is silicon nitride, and all the dark stuff in the back is a vacuum. So it's freely suspended. Into this, we want to put an atom. Let's just get started talking a little bit about the physics of one atom in a waveguide like that. We're going to have the atom such that we've calculated, and we're on our road to this kind of a value, where the atom in the excited state would emit with a rate 10 into the waveguide and only rate 1 everywhere else. This gamma prime is the rate everywhere else, and gamma 1d is in Roy's polarium, the rate along this along the waveguide. What that means is if you have a single atom like this and light's propagating, this is a waveguide like an optical fiber. It's really small, but like the atom's really big. It just would go forever in the ideal case. And if you put one atom there, this ratio means that this system, one atom in the system, would reflect 90% amplitude. It would attenuate 100-fold. So that's good. That's one atom. In terms of a cavity QED kind of things, if you put mirrors around this atom, like Misha Lukin's group has done in collaboration with Dielectrics, you could get Rabi frequencies of 10 gigahertz. So a single photon would cause nutation at 10 gigahertz. And the critical photon number would be 10⁻⁷. In that graph I showed you a little while ago, after my adult lifetime, we thought we could do 10⁻⁵, and this is going to be 100 times better. So what is it that's special about this single atom? Well, we have a band diagram. This is periodic, so we apply Bloch's theorem and we get bands. This is called a dielectric band. It's called an air band, and we get a band gap. And if you look at two frequencies, those two frequencies near the band edge, if this frequency drives this mode, that frequency drives, you get the same K. So you can have two frequencies which turn into the same length scale. You can't do that in the vacuum. Atoms have discrete levels, and you want to do trapping at one set of levels and quantum optics with another set, and those two length scales don't match. So it's hard to extend one atom, one photon physics to many, many atoms. And this is a great trick that's called wave vector. Furthermore, if you go to the band edge, the derivative goes to 0, and it's 1D device. There's a Van Hoff singularity, and the density of states diverges. So you can make this gamma really, really big compared to what you would have thought for conventional kind of optics. And that leads to the possibility, if we trap not one, but lots of them, that's how we're going to make polarium. Lots of atoms along here, every one of them is reflecting 90% of the light, so they're all talking to each other by photons just bouncing up and down this thing like some kind of a quantum pinball machine. So that's the idea in qualitative terms. More quantitatively, we've calculated lots of things. The qualitative idea is that light transporting down here, one atom is already a big deal. One photon's a big deal. And so if you have lots of atoms, you're going to get a really rich quantum many-body system of atom-atom interactions mediated by photons, or on the other hand, photon-photon interactions mediated by atoms, which I'll tell you a little bit about. So I think it's really a new playground for achieving quantum many-body physics. This is going to be necessarily non-equilibrium systems for photons, atoms, and even phonons. So just to give you a kind of toy example, we're working on others, but this has already been published, led by Derek, again, Misha's student, and Ignacio Sirac. Imagine we have atoms trapped like this. So this is a 2D waveguide, but not a photonic crystal. Let's just be simple, and it's 2D photon. This guy has a wave, this guy has a mode, and then we put them together. The modes hybridize, and we want to use the symmetric combination so the light's bright where the atoms are. But we're going to let the atoms be completely free along the axis. Normally we want to constrain them in all three dimensions, but now let them be completely free, and then we'll shine light in externally so that this thing is like this, and then a plane wave comes like that. So the excitation brings no length scale. So the atoms are going to start to scatter. They're going to push on each other. They're going to spill forces. The gamma 1D means the scattering large can mean the scattering can be really large compared to free space. Once these atoms get to be pi apart, it's super radiant, and the scattering rates go up if there were n atoms infold. So the really large radiation pressure forces along the axis. The question is, what happens? You put these atoms, and they're not free to move. They're free to move here, not trapped. And what you might think in a calculation is that you shine light on it, and it just blows apart from the radiation pressure. You can't do that. The Green's function for this thing is this atom talks with any atom to infinity. Infinity for this thing means until retardation is important, and that's about 20 centimeters. And this thing's going to be 100 microns long. So an atom that tries to fly away can never fly away. All the interactions of level shifts and enhanced radiation rates in Roy's polarium are pi periodic. So it can't fly apart. That's your first intuition. What happens is, if you shine light on and you're detuned far below resonance by 15 line widths, this is the fraction. What's this spacing? Modulo 2 pi. And what happens is, as you go closer and closer to resonance, there's 150 atoms, and the atoms, what this picture means is the atoms look like this, and they begin to compress. So it forms a lattice, these atoms. In the far detuned limit, this dashed line is universal. It goes just as 1 minus 1 over 2n for the lattice constant. And so these atoms go like this. They compress. They've compressed so much now that they wrap around when you go just below the resonance to the peak. This is the peak in the dielectric constant. You think of an atom as a dielectric. It has a peak in its dielectric constant just half a line width below resonance. When you go to resonance, the whole thing unwinds. There's no dispersion. This thing is bound together by the dispersion. The phase shifts along the lattice. And then as you go farther off resonance on the blue side above, this thing breaks in two pieces. So it unraveled, went flat, just uniform lattice constant, and then breaks, and then it finally heals back to this universal limit. Is it really a lattice? Yeah. If you look at the black curve, as you go towards resonance, the refractive index is getting larger and larger and larger, dielectric constant. And these are the 149 phonon frequencies of this system at each of these points. And the frequencies go up because it's really being bound self-consistently. Nobody told the atoms how far apart to be. So it's self-consistently bound into the lattice. And then you go to resonance where this dispersion goes away and the lattice melts. Is that a phase transition? It's a non-equilibrium system. Smart people haven't figured out exactly what's happening. And then it goes off. Now, how would we probe all this? Well, go talk to a condensed matter physicist. If it's really a phase transition, what you want to do is measure transport. So in our case, that means send light in, send out light. In their case, it means hook up a voltmeter. Give me a break. You go in, you go out. We do serious stuff. So how would we measure that? Well, these are the transmission spectra, transmission in red and reflection in blue. It doesn't really matter the details, but you saw that the lattice was changing, and those changes are reflected in transport measurements of the system. The place where the lattice broke into these two halves actually looks like this. There's this phased array over here of super-radiant emitters, and over here super-radiant emitters. But when they face each other like this group of atoms is like a good mirror. This group's like a good mirror. But this set is completely out of phase with that. For every pair here, there's a pair that's minus. So this is superradiant, that's superradiant, but the atoms arrange themselves into a subradiant state to avoid all this extra light that's scattered around to push them around. So it's a really rich, this is classical dielectrics. We haven't taken into account that the atoms can absorb and emit only single photons. We haven't counted the center of mass, degree of freedom in the atom. So I think it's a rich, Derek Chang and Ignacio Sirac are working on extensions of this to the true quantum domain. Okay, so it could be interesting. That's the kind of polarium that we know about so far. If we drive the system not in the dispersive regime, so the atomic frequency here, then we get propagating waves. If we put the atomic frequency here, then we get localized modes. It's just like trying to drive a conductor below the plasma frequency. You get a localized excitation that has kind of skinned up. This photon atom complex just sits there. It's stated a different way. There's only a real component to the Green's function of this system because there's no propagating dissipation. If you put another atom over here, these two atoms can do spin exchange. if their clouds overlap. And so in this case, there'll be that coherent evolution of one atom going to the ground state and the other excited state, and virtually exchanging photons because there's no propagating modes in this, and there's some spin rate at which that happens. There's collective dissipation, super and subradiant modes I already mentioned. That's gone. We're inside the band gap. That's exponentially suppressed. So what you get out of this, if you put a lot of atoms there, each with its own little volcano of a photon cloud, is a complicated spin-spin Hamiltonian. So we can do quantum magnetism, again, not in an equilibrium phase, but non-equilibrium driven, where this J coupling can be megahertz. And we can, apart from this, we can do essentially arbitrary spin-spin Hamiltonians. This is this length scale, and if we just tune relative to the band edge, we can change that. So that's in terms of the internal degree of freedom. But in terms of the external degree of freedom, this is a force. So the spins experience very large, the atoms experience very large spin-dependent forces. That's just the quantum version of the self-organization I just told you about. And the kind of state-of-the-art at how you solve this is Derek Chang with James Douglas doing two atoms. And what you can get are the two spins of the atoms will dimerize. They have to move into a singlet state. So you'll get into that self-organization I told you about in the classical regime, and the quantum regime turns into dimerization and entanglement between external and internal degrees of freedom. What it looks like for all those modes, we don't know. Okay, so back to polarium. That's kind of spin-spin. That's the atom part of the story. But those atoms have spin-spin interactions, and that's the material system through which the photons propagate. So if they're doing something funny like spin-spin interactions, that means when this guy excites it, it changes the energy of the other spin. And that means that the dielectric constant changes. So if you have this atom get excited, well, that excited through spin-spin interaction shifts the energy over here. And if the resonance frequency shifts on the dispersion curve just of a linear dielectric, the dielectric constant changes. So you have non-local. One atom gets excited, and the spin-spin interaction causes another atom to shift its frequency. If there's a photon over there, that photon then propagates with a different dielectric constant. So qualitatively what happens, again, this is on the archive here, the papers. Nobody really knows how to do that for more than two photons in special cases, but what it means is that if you have two photons propagating, there's a bump in the dielectric constant. If I choose J to be positive, there's a bump in the dielectric constant, and that binds photons. If there's one photon, there's no bump. If there's three, we don't know. So this pair of photons propagates bound. If you had separated the two photons in the beginning, say the way you launched them in, then they won't have a relative coordinate that matches the minimum in the potential, which is, say, the maximum in the dielectric constant, and they'll oscillate. So these are two photons propagating, and you can see in this a relative coordinate that the photons oscillate back and forth. They're really a bound state. It's not a photon, it's a polariton. It has a mass. And so what it looks like is they propagate. Two photons look like this, and they oscillate like that. And the question is, well, good, that sounds like fun. What happens if I put 2, 4, 6, 8? What happens if I put a coherent state in? Is it stable, or would it fragment into photon pairs? We don't know. But it sounds really interesting new frontier for doing atom photon physics. We'd like to do chemistry. For God's sake, what does my life come to? Linear chains of molecular, I told you how to do a pair. I think we know how to do that in the lab. We know how to do another pair. This is a long-range interaction, which in work with Ignacio Chirac's group, we know how to make any two distances in the lattice, any two spins, have an arbitrary sign and magnitude. So we can make interactions between this guy and that guy, that's their spin. Between this guy and that guy, that's their spin. Or indeed between that one and that one. And so we're really looking at your polarium. There it is. All these atoms trapped. If we can get 50, we can do really neat stuff. And inside one of these alligators, that's a real alligator. That's about a third of the picture of an alligator. So we really will propagate photons and try to do this kind of thing. And so it's a quantum dielectric. It's not the quantum optics of linear dielectrics, but it really is a quantum dielectric. And it's not your first paper, but your second paper. There's really a large community worldwide working on that, where in some unit, there's the material, you eliminate that, you get the dielectric constant. This is a dielectric constant which depends on the number of photons and the separation. And the dielectric constant is different for this material for 1, 2, 3 photons. 1, 2 is what we know how to do so far. So I think that's a really exciting prospect. I should note that this kind of realization of polarium in a different setting has already been achieved by Vlad and Dielectrics group at MIT in collaboration with Mr. Lucan to have photons try to bind, have attractive forces between massive photons by using Rydberg excitation. So it's really a very active and I think exciting time to do nonlinear interactions, not 1, 2, but we're ultimately going to do these into quantum many-body systems. Okay, now the hard part. Casimir-Poldr potential, we got to calculate. I showed you there's alligators and atoms in there. How do you really do all that? Well, we've had to work hard to do that, but we've used really important papers from Girish Agarwal years ago, and then in the modern time, what really is it we're supposed to be calculating and how do we do it in these complicated dielectrics? And as I said before, there's really no analytic way to do it. So you get stuff and you have to think about it, and looking back at your paper, well, if we had a modal expansion, what could we look at and what are the right quantities? So this is what we built to make this real. This is the alligator here. And we've had to overcome a lot of problems, which I won't dwell too much on. I just want to show off our young child. This is the alligator. This is 250 nanometers. The lattice constant is about 350. We've got impedance, taper it to impedance match in and out. We put anything like that, we can efficiently couple in and out through fiber. And then we got to put atoms in it. So how do we put atoms in it? We make a trap in the spirit of this work by, again, Lucan and Dielectrics group. We cool the atoms to pretty low 30 microkelvin. We trap atoms. This is the dielectric coming out of the page at you. We trap atoms here, 100 nanometers from the surface. Light propagates again into the page. This is what the trap looks like. It looks wiggly. Well, this is a three-dimensional calculation of Casimir-Poldr. You got to be able to calculate this through the whole unit cell. And 10 years ago, people just didn't know how to do that. So that was a big impediment. Trap an atom there. This is the block mode near the band edge. And we want to look for atom physics again, the way they interact by measuring transport. So the thing we want to know in the beginning is if we put an atom in there and it radiates, what's the reaction field on the atom? We need to know the real and imaginary parts of that. The real part is just a level shift, different than the free space lambda. And the imaginary part is enhanced or inhibited decay. We're going to want to know for 2 atoms, and I won't talk too much about that, but we know that. So just for now, 20 minutes? Who had the bell? I have 3 minutes by my timer.
I didn't have a bell. I don't know what bell that was.
Oh, there's no bell. Good. So this is tune the frequency and you come to a band edge. And this is the self-Green's function for the atom. And I won't say much about it, except this is a level shift term. So for a single atom, it changes its local radiation field. And this is the dissipative part. So this is imaginary part of the self-Green's function. And what we want to do is put an atom frequency out here in the propagating bands. So in this case, we're below a band edge, and we want to look at just propagating physics. And then we want to tune the atom frequency into the band gap. And what should happen? What should happen is the dissipation into the band, into the guided mode goes completely away. There's no emission into the guided mode, but there are frequency shifts. Of course, we're not going to tune the atom. We're going to tune the structure across the atomic transition. And this is the kind of takeaway message about, well, this polarium and really interesting quantum dielectrics. If you go into here, the ratio of essentially the real to the imaginary components of the Green's function goes to infinity. This term is exponentially suppressed. So the spontaneous emission into free space or the guided modes, and the guided modes gets exponentially suppressed. So we'd like to measure that. Let's look and see if we can measure these curves when we go into the band gap. And yeah, we can. So this curve is the dissipative, cooperative, collective emission in these red points. And these points, this is the superradiant emission, this is inhibit emission inside the band gap. These are dipole-dipole spin couplings here. Over here, they're out here too, but over here this ratio is supposed to be exponentially large. And when we get this all right, we think we understand what's going on in terms of a not so simple model that goes beyond conventional optical physics, I would say. Exactly where the band edge is, if I give you a theory, then it's easy to find out, but if I give you a piece of dielectrics, it's kind of hard to find out. So that's our kind of current uncertainty. And so we're able to measure, just like in your paper, these sub and superradiant modes, these dipole-dipole interactions, level shifts, as you call them, and we think we can really harness them for really interesting physics. One is the Einstein coefficient in free space. In our current structures, that one is the emission everywhere except the guided mode is called the gamma prime, and that's about 1, 2. But we're working to take our atoms from here. This is the dielectric, and the alligator's coming out of the page. And by adiabatically changing the trapping potential, move atoms into here. And this is a hard calculation, believe me, that Chen-Lung Hung did. But we ought to be able to do that. And then this number goes to 5. And then the measurements I just showed you, instead of looking like this down at the dirt of 1, are going to go up like that. And we move going to the gap like that. So this dipole-dipole interaction ideally will be free of the guided mode losses. And that says we'll do spin-spin physics where the rates are 20 megahertz. So it's just completely different than the normal kind of paradigm. So that's what we're after in this. In the next device, which we haven't built, this is with the device we have, if only we can move the atoms in, this number will go to 50. It's just going to be a completely different way to do spin-spin kind of physics and realize this quantum dielectric. So we know how to do all this in 2D. It's in this paper. We know how to trap. We've designed real traps. What's the spin-spin physics look like among the atoms? It's got to do with stuff which, oh my God, a kinetic matter physicist needs to know. Molecular physics, I'm learning chemistry, and now I'm learning kinetic matter physics. Anyway, so we know how to put atoms and trap them, and then have band edges where we can do this interaction that I described to you. And I think it's just a whole new world for rich phenomenology. Quantum magnetism, topological atom-photon matter, dissipative quantum phases. I'm really interested that we'll have 100 by 100 slabs, and we'll have 2D molecules propagating around and colliding and doing chemistry or whatever they want to do. So that's what we're going for. This is kind of in 1D. There's interesting stuff to do. This is artist comparison. A postdoc knows how to do these graphic things. I don't. The idea is a new paradigm, and it's quantum dielectrics. Where the band structure depends on single photon kind of physics. The photon-photon interactions depend on single photon, 1, 2, 3, for propagating modes. And to really realize things that I couldn't have dreamed of, when I first met you in '77, that we really can do in quantum optics, not onesie twosies, but really powerful quantum many-body physics. So that's what we're trying to do. And to conclude, happy birthday. Everybody knows that. It's really amazing what you've done. But beyond the science, I'm really inspired by your life. I've really, what I view high integrity, generous to me since I was a graduate student sitting next to you in a summer school in 1977 in Italy, riding with you, Rodolfo Bonifacio, going to an opera, wondering when my life was going to end. And your curiosity is just boundless. And so refreshingly, it's about the physics. It's not about what political advantage in this modern world. There's so much of politics. So what I can say to all of us is it's easy to fail trying to follow your example, but we all have to try. And thanks about the dielectric tip.